underlying concepts. And then the last lecture would have been the tutorial, in the sense that one particular example we take and do a neural network based method, so that people, whatever they get an idea from the conceptual side, they implement, I mean, get a better idea, like the working thing, like with a tutorial thing, like what Lucas was doing right now in a sense. So yeah, so basically, if you want me to finish in 3 class, I can just give the tutorial thing. I can give the slide so people can try it out. That is also fine. Okay. So all right. So let's start. Share screen. Okay, you see my slide, right?
Yes, please.
So yeah, excuse me. So we discussed about don't get too jittery about so many mathematical terms, but what we said, like the data you have, the experimental data you have, and out of that you have some input or feature variable. We discussed that in the previous class. So you have a number of feature variable that you want to use in your these machine learning techniques, and you want to find out some target, right? There's something like, if this classification scheme particularly, there you want to do like signal to background discrimination, or you can have, so signal to background, obviously that is sort of binary classification, but you can have multiple classification, right? One signal versus multiple background. So so you want to project, you want to map you from this feature space that you have to this target space, in a sense. And so this classification, what we do under the name of supervised learning. So there is finite, I'm basically repeating what I said last time. So there is a finite set of labels, that's what the supervised means, like that what you want to get. And that is mostly done using Monte Carlo data, mostly Monte Carlo data. When we come to the example, then it will be clearer to you that what we are saying. So mostly we use Monte Carlo data sample to do this classification scheme or training, testing, all these things. And later you apply to the data. And sometimes if like where you have a clear cut, what we call control sample, where if you can use data event like in some sideband. For example, you are looking at, I know in Hebbian analysis, sometimes you look for phi meson or D or B meson or something related to your signal for Quark-Gluon plasma. So you get an invariant mask, but then you get also the sideband, and the sideband is not, it cannot be your signal, and that you can take as your background and for doing this machine learning training. So in any case, for binary classification, you have 2 classes. Here, just take the example of Higgs signal versus background, all other standard model background. You can also have multiple class that sort of that is given there. Okay, so so in case of regression, you are basically dealing with you want to function. It's like y equal to fx. Like you have the data and you want to find out a functional form. And there was a question last time that I think impact parameter. Yeah. So can we model the impact parameter of the event? And the answer was obviously yes, depending on what is that variable that you want to model that impact parameter on. So we will have an example, something for the Atlas and CMS experiment. So that goes in the regression technique. Okay, so that was the supervised learning. Basically, you're talking of classification and regression. The part that we don't deal so much, but that is where you don't have a specific label. You let machine learning technique to look at the data and find on its own some sort of structure, some sort of shape, some sort of, so things like clustering, where you partition, you divide the data into several group, contagious group. And also the other thing, you do dimensionality reduction, where you start with a sort of somewhat complex representation and you go down to lower dimensional. When you go to lower dimension, it's less complex. And I gave the example of sort of in the 2-dimension, we express XY. I mean, when you go from Cartesian polar to Cartesian coordinate to the polar coordinate, right? So you get the R as the only independent variable because theta is a cyclic coordinate, and all right. So this reinforcement learning, this is something we will not use in high energy physics, and I would just keep that through. And then I come to the very, so the idea of this lecture, as I said in the beginning, you can take up any particular package. There may be multiple packages. These days, quite a few multiple packages. I don't know how many of you know. There's a toolkit for multivariate analysis, TMVA. There is in root also this machine learning methods are there. Deep neural network method is there. Google has this Keras software, and then many software around to do this job for you if you don't want to write. But what is more important, you can use the software as a black box, but this past 3 lecture, the idea is to kind of break that black box to you in a term, in a language that you will understand, and you already know from statistical, from your data analysis technique, or that you have been using, and probably you just didn't realize that. Okay, so how does the supervised learning works? So you see on the left-hand side is what you have given from your detector. That's the data you have. And from this data, you want to sort of find out the Higgs signal, let's say from the all other standard model background. And so you see what you have, this HX W, and this X, as I said, these are so-called the feature variable, the input variable that has that discrimination power to distinguish between the signal versus background. And you are, so individually, like you, most of you would be, or pretty much all of you would be knowing cut and count analysis, where you take a set of selection variable and you put some cut, of course you optimize and then you do, but that's probably not the most optimal way of distinguishing signal to background. We do machine learning technique, various machine learning technique, and this W is also those parameters. So X is given by your data, and W is the so-called the weight parameter. These are the adjustable parameter, and you are basically doing a multidimensional optimization. At the end of the day, this is a multidimensional optimization, and then you will ask me, what is that we optimize on? Okay, so we define something called loss function that will be clearer as we go further down the slide. And that is what we want to optimize. And since it is supervised learning, you have the label, you know what you are calling signal, and you know what you are calling background. And in the process of this optimization, in the process of, you want to sort of see that what you are predicting, how far it is away from your true label. Okay, so that's what the loss function will be called. So you design a function with adjustable parameter, you design a loss function, find a set of best parameter which minimizes the loss function. So as you can see in this 3 bullet point, all that you know, all that you want to learn about machine learning is pretty much there. Okay, and obviously it is not like in a 2-dimension, as you see, it is really multi-dimensional hypersurface, because you have many parameter, many input variable, and correspondingly that many adjustable parameter you have. Okay, so so how do we get this best parameter and how do we establish these are the best parameter? You use label training, what you would be all knowing if you have done either boosted decision tree or neural network, you would be knowing that there is sort of two step. There is a training and testing step. And so in the training set you want to sort of train the network, and you want to optimize on the loss function. You adjust the parameter and find out the best possible parameter with the minimum loss function. And once the parameter, you get a stable set of parameter, then you don't touch on then you don't tamper with that weight function, and you take it to the final data, or sort of what we call the testing data. Can you hear me okay? Or if there is any background noise other than me you hear, then just to, do you hear me all?
We can hear you.
Okay, fine. All right. No, I'm working from home today, so that's why I just. All right. So, so here is a sort of, you can say, master equation. It's a little bit mathematics, but don't get sort of nervous about it. It's basically quite simple. So let's look at the function. So xi, as I said, this is a vector, like n-dimensional vector. And then I equal to 1 to n, you see this is the number of data point, right? So in the case, if you are using Monte Carlo, I said mostly we use Monte Carlo data to train your machine learning technique. So that basically over the entire data set, whatever your training data set you take, that you want to optimize on, train the network. And then W is, again, it's not a single, it's a vector of weight vector, and that are optimized on. Yi is basically the output that you want to get at the end of the day, whether it is signal like or background like. And so that term is what you want to optimize on. The so-called loss function, L stands for the loss function. And then you have the second part that is not always used, but sometimes it is used. If you have a very complex function and a complex problem and you want to little bit simplify. So this is what we called, like if you have done in classical mechanics, sort of solving the problem, you introduce the Lagrange multiplier method. So this is this lambda is a Lagrange multiplier. Basically, it's a model regularization. You introduce certain kind of penalty, so certain values of the weight factor, you want to control them. Of course, as soon as you introduce some kind of control, you introduce certain bias into the problem. Of course, now you'll say, well, is it good or bad? Now, certain amount of bias, if it solves the problem, if you can control what we will learn soon called variance, that's perfectly acceptable, as long as that does not overshadow over the variance. A little bit of bias is okay. So that is possible, and that is used sometimes, particularly in the case of regression method. So as you can see, at the end of the day, you have the learning is cast as an optimization problem in the n-dimensional hypersurface. So we use largely two loss functions. One is square error loss function, or called square function. And also, if you look at this, and it can remind you something you have learned already, it looks pretty much like a chi-square, right? Of course, it has to be divided in chi-square. You get you divide by the okay. In pool case, you take the sigma square in the denominator. So this kind of error loss function is used regression. And then for the other one, we use a classification called cross entropy function. So where it's given as minus y log. So what is y? Y is, as I said, it is the if you have a two class, let's say in the classification case, y is only two value it has, 0 or 1, right? So assuming signal is 1, background is 0, so it has got two value. Like at the end of the day, you would expect to have some distribution. For signal case, it should peak around 1. In the background case, it should peak around 0. And so that looks like a binomial distribution. If you remember that, so you are doing this toss a coin, head or tail, and then you get what is the probability of head and tail, and from that, if you want to figure out what is the total probability, like you do several times, and then you want to find out the probability. So there you see y and 1 minus y, right? So one is the probability of finding signal, other one is for finding the 1 minus of that is the background. So yeah, so these are the two loss function we largely use, but then there is sometimes people talk of hinge loss or 0-1 loss, but mostly we don't deal with that. And this, by the way, this mathematical concept that whatever I'm telling right now, this is mostly taken from this book by Bishop. It's called Machine Learning. I'll give that reference at the end if you want to look at it. Okay, so just a little bit of digression, a little bit about the maximum likelihood method, and yeah. So I think you might have used maximum likelihood method like on-bin maximum likelihood method or bin maximum likelihood method. So that one, basically you have the observed data distribution and you want to describe that observed data distribution in terms of some model, in terms of some model, a composite model, and the composite model you may have again signal and background, and that model obviously described by a set of parameter. Some of the parameter you might be directly determining from the data fit, and some of them you might be fixing into, if you know that some value you can fix to, you can do that. So again, this is the way the likelihood is given by this the Bayesian the probability, and if you have a data point, you model as a product of I, and largely we turn this likelihood into a log likelihood. For obvious reason, the product will turn to a summation, right? If you take a log of this, the log of the product will turn to summation, and it becomes much easier to sort of differentiate. So it is easier to deal with that. So we call it log likelihood method. Okay, so so in the general parameterization, like if you want to, in a log likelihood method, you want to estimate the parameter. The way we do, we want to maximize the likelihood, and if you want to, if you do the negative log likelihood, then you want to minimize negative log likelihood, and that's given by this formula. And taking the minus negative log, your product I turns to a summation I log on the pi. Okay, so 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 here is the about a little bit about the square loss function. So if you have this linear model given by this h, x again is the input parameter or the feature variable, and then w is the weight vector, and this is the way it is presented. And from that, you can find out the likelihood function, sorry, the square loss function, half of sum of I, yi, and so yi is again depending on what you want to do. Like if you are talking about the regression, here it is not classification like 0, 1 or C1, C2. Here you have a function, right? So given this distribution, there's a question of impact parameter question asked day before yesterday. That is what you want to find out in the y-axis. X-axis is what is the function, you know, that the independent observable that you want to use it. So so here what you see in the plot is the price of you know, housing as a function of the square feet for some particular city, and you see, somehow it goes up depending probably which part of the city you are in. Um, and yeah, so this kind of square loss function is used in the linear regression method. And you can go from the linear regression to, you can also represent that in a matrix form, so-called, you have the covariance sort of the matrix, and then the diagonal term and the off diagonal term, and those are mostly what we know in terms of covariance matrix. And finally, you get the target vector y, n-dimensional vector. Okay, so right. So given that you want to find out a loss function yi minus hxi, this square loss function. So once you present the hy as the xw, then you can represent the loss function as in terms of this in terms of the target vector formulation like this, and then you can minimize. So the important thing here, from data, what you get from the data, you get the x. Y is what you want to determine. Y is what we want to obtain at the end of the day, the functional dependence, and then W is what you is the part of the optimization. These are the weight parameter that you are trying to optimize. So yeah, so when you want to minimize with respect to W, because that's the parameter you want to optimize on, so it can be expressed like this. So yeah, so there are a few things where the regularization, the extra term, we're talking of the Lagrange multiplier in this this model regularization, that comes into play if you have because realistic problem is can be more complicated than simple thing that where we talk of the variables. They're not correlated, and we know that correlation is very much there, and sometimes you have a very strong correlation, and that leads into trouble. And that can be, in that case, you have to add this regularization term and try to kind of constrain some of those parameter, the weight parameter, to. So in the process, you get some bias, but it is still acceptable bias. Okay, so here is a real life example of regression method. Again, going back to what the question was asked, that imagine that something like your impact parameter you have in the y-axis, and you want to model it. You want to use the linear regression method to find out the functional dependence. So here you see the PT of the reconstructed jet energy, basically the transverse energy, jet energy, and EM, even that is the electromagnetic component of that, as a function of so-called the primary vortices. I mean, this is an example from Atlas, and here the linear regression technique has been used, and yeah, so one gets this average slope, as you see in this expression over there. So something similar, if you want to do, you can use for impact parameter, obviously, like whatever your dependence, whatever the independent variable you want to use it. Okay, so right. So yeah, so let's take the simplest example, that you have a linear, so y equal to fx, but it's a very linear dependence. So in that case, yi can be expressed like this, mxi plus ei, and from that you can go back to what we know in a chi-square optimization method, chi-square minimization method. We can get this term, And also in the likelihood method, you know that this likelihood method is equivalent to a chi-square method, basically. And yeah, so at the end of the day, you have this yi minus mxi whole square. Okay. So that is like the square loss function comes into picture. All right. So all right. So let's take the case. Here we are taking the case that we're assuming that linear, the dependence between your that independent variable versus the dependent variable that is linear, but that doesn't have to be the case always. So you can also use, instead of a linear function, if you have a nonlinear relationship, you can take a generic basis function given by like this. And this we can use as a polynomial basis. You can use a Gaussian basis. But whatever basis, you know, from central limit theorem, you know that finally you get the expected behavior. So here you can see that something, you have a distribution y, and so y versus x, but you see the data points are described. So this the blue circles, empty circle, you see these are the data point. And then out of this data point, given the y, you want to find out y as a function of x. All right. You know, so whatever basis function you start with and you want to optimize, finally you will get y like the way here you saw. So if you have a data point of something like this, whatever basis function you start with, at the end of the day, you will end with a linear function. So similarly here, you end with a kind of a sinusoidal function. Now, so you'll say like, okay, you have a data point like this, then how how on earth I got into this linear function, this kind of sinusoidal behavior? I could have gone something like this, or like, so this is an important slide. You could have, so the thing is, like you can see that the data distributions are given, or so-called the field blue circle, those are the data distribution, the sample distribution. The true function, or the closest to the true function, is this green line. Okay, that's sinusoidal behavior. Now imagine if I would have used a straight line, you know, sort of a model, I would have used a straight line. Clearly, you see that I am basically not able to, only one or two data point I'm able to describe. So this is really what we call underfitting. On the other hand, if you look at the extreme right, now, so in case of underfitting, what you'll have a large bias. Okay, you'll have a large bias. Now, in the case of the extreme right, what you have, let's say I will say, no, each of the data point, I want to minimize my bias to 0. Okay, so I want to have a function which really touches upon each and every point, and then you get a what we call overfitting. Obviously, your bias is very close to 0, but what we call variance will be really large. So that's what you see on this particular slide, that the function that we get this sinusoidal behavior, that is a good average behavior, and it has got an acceptable both bias and variance, which we'll describe in the next slide. They are kind of minimum, and that's what we want to achieve. Okay, so the total area, total error can be described in I'm sorry, yeah. It can be divided into two things. One is called bias, that sort of how much deviation you have from the actual model versus that your fit that you are getting, the actual data versus the model that you are fitting. So in a underfitting case, you'll have large bias. Okay, you may have low variance, but you'll have very large bias. Now, in the complex, I mean, if you try to overfit, so in that case, systematic from the data versus your model, there will be very little deviation. I mean, the difference between them will be very small, that is low bias, but you will be very, very sensitive to data, and which should not be the case. At the end of the day, I mean, again, I go back to this thing which is obtained from Atlas. This is at the after the regression is done, but it is not so beautifully distributed. Like if you look at the so-called the sample or model distribution in the beginning, it was not that each of the data point were just sitting on the straight line. This is after the regression is done, and you see the beautifully this linear relationship. So yes, so in the overfitting case, you will be very, very sensitive to the data because you want to get the least possible bias, and then you remain very much sensitive to the data, right? Because you want to touch each and every data point. So that leads to high variance. And so expressing it in mathematical term, you can see you want to find out the loss function or error function described by like this, okay? And this can be expressed, this is like the expectation value of y minus y average whole square. And then you have the average y minus the average h, which is a function of x, obviously, that square. And this is what the bias term is. Like if you want to minimum bias, that means your function versus your data, they are really one top of each other. And in the variance, you have the function minus the average function, so sort of that expectation value you want to take. So this is variance. Okay, so noise part is something like that intrinsically there. Okay, so what do we do in the actual optimization of this machine learning technique? We want to go for the minimum possible bias. So there is a kind of trade-off between bias and the variance. Okay, and so the intrinsic noise in the system, we cannot avoid that. Okay, we cannot improve with machine learning technique. Okay, so on the other hand, if you have more complex model, that will be, you will capture more data point, the lower will be the bias. So your Y bar will be close to the S bar. But if you go to the more complex model, you will remain prone to a tiny deviation into a data point that will leave, sort of, it will be too much of unstable. So it will bring in more variance into your model. So yes, so finally, what you need is given in this plot here. That with one hand you want to minimize the variance, bias. On the other hand, your variance goes as you want to get into too little bias, your variance will go up. So there is a kind of competing thing. And the real scenario that you are really optimizing is somewhere in between, where you have, sort of both bias and variance at an acceptable level. They're at their minimum possible value. Okay, so this is the regularization term. In general, we do not use it, but only in the case when you have there is a kind of correlation among the input variable, the weight parameter and the model parameter, that will introduce some kind of instability into the problem. So we try to introduce some kind of normalization or regularization term into the model, which introduce some bias, but it is still acceptable. It gives rise to acceptable variance. Okay, so the bias term is lower than the variance term. I mean, obviously, if it gets more than the variance term, then this is not a good regularization. Okay, so right. So now comes to the thing that you have mostly know. In the classification scheme, mostly you do two-step training and testing, but in a so-called regression, we divide into three. So there is a training set, there is a validation set, and there is a testing set. In a classification, just two set. Here you have one additional set. So what do you do in the training set? In the training set, so again, like your question of impact parameter. So whatever distribution you have, the input distribution you have, and so you want to find out the y, and you see in the training phase that blue cross that you see, that is your data distribution. And at this stage, you try with different fitting function, and you try to find out for whatever optimization fitting optimization you are doing, you want to get that model parameter. And then in the validation set, you check that fit model parameter and that fit model and using the validation set. And there you can try to optimize, I'm sorry, you see the performance, and if needed, that some of the parameter can be tuned, okay? Some of this H parameter can be tuned. And so it's like an interim step, initial training and then validation. After validation, you are confident, then you go to the final performance test, where that hyperparameter you do not touch anymore. So between training set, you are more or less there, but there could be a little bit of change to some of them into the validation step. And finally, you go to the test step. Test step, you do not touch the hyperparameter. Okay, so here it says like how in the training sample you get the prediction error versus model complexity, and then as you get from this sort of, this is the low variance high bias side on the left, and on the right low bias high variance, and in the middle is what you want to achieve, reasonably low bias, at the same time reasonably low variance. So that's what you optimize a little bit the hyperparameter, and in the validation sample you achieve that. Okay, so that was about the regression part. So where we talk about three-step training, validation, and testing. In the classification, you mostly have two steps. Okay, so here you see kind of example that that why we want to go to the machine learning technique or more complicated analysis. At the end of the day, all the high energy physics experiment, the physics, whatever physics we want to extract out of that, it's not so simple. I mean, so you could imagine that what CMS and Atlas experiment found in terms of the signal of the Higgs boson. I mean, the Higgs boson was very much there earlier. It is not that it appeared one fine day of 2012. It was very much there, but you didn't have that kind of environment. You didn't have that kind of, because it's very small cross section, you know, the probability of finding that. So, so you need to have that kind of data where you can figure it out. You can find out this small signal coming because of small cross section. And so here you can think of like this. So you have two sets of field circle, red and blue, and your job is to kind of separate the two class. So largely what we do, x1, x2, think of two input variable, and you have been doing all along. We're applying some COT, we call it selection COT, selection criteria. So I accept, let's say, if the job is to select Y, reject X, you will say if X1 is greater than X1, that whatever that vertical line says, and as well as X2 is greater than, again, that horizontal line, whatever the value, that is what you will do. But then you see in the process, you'll definitely pick up some wrong event in your sample, and you will also lose some of the right sample. You will be reject them, right? So that's in what we call rectangular cut. We do somewhat better. If you go to nonlinear discriminant, you can see, like, turning the rectangle to a circle, you get a little bit less of this kind of less number of background in your signal, and less number of signal getting rejected. So the trade of the job is to find out best possible efficiency and the best possible purity, or least possible background. Okay, so what you will see, so-called the receiver and operator characteristic curve, or ROC curve, or ROC curve. So that is what you want to optimize on. And going from a simple sort of nonlinear thing, you can even go to more complicated, as you can see, the what we call decision boundary. Obviously, you have to be very, very careful. As you see from the previous slide, in the regression case, let's go there. Yes, you definitely don't want to, what you want to achieve, you want to achieve what is there in the middle. Neither you want underfitting case, what you have on the right, left, nor you want to go for the overfitting case, which is on the right. Similarly, that is in the regression case. And similarly, in the classification, what you want to really achieve, not the what you have in the bottom right. That's really like overfitting. Okay, that's really overfitting and highly sensitive to little bit of variation in your data distribution to skew up your classification scheme. What you want is something closest to, let's say, the top right. Okay, and that's why you know that when you use machine learning method, I suppose some of you have used, or maybe all of you have used. So you see that one of the important step you have what we call checking up overtraining, and the overtraining is really something you want to avoid as much as possible. Okay. So it will be highly skew of your thing, and it's not good. So what you want, that training versus testing, there should be sort of in two independent subset. You should get similar output for your machine learning method. Okay, so so now we go to a little bit about this the underlying principles that goes under this classification scheme. That what we saw here, but that is in mathematical term we describe here. That basically the decision boundary is defined by this this expression here. That if you talk of in the rectangular chord based selection, it is basically you have a number of this x, the feature variable or input variable, and then for each of the x you have certain criterion which kind of either accept or reject, sort of, and then you obviously at each step you will lose some signal, right? So that is why a rectangular cut method is not the optimal method. It's a robust method, but it is not the most optimal method. And evidently all these days, pretty much I would say all high energy, physics experiment, maybe I'm true, or most of the high energy physics experiment are using a machine learning method. Okay, so yes, so this is what you have. That why you not use the so-called the least square method. Um, so here, what you see, the linear classifier with least square method, and so you have this blue circle versus the red cross, and you want to optimally discriminate that. And the best method, the best method obviously will give what is the blue line shows you, but sometimes you will get, it is not like you will get 100%. I guess none of the method will give you 100% signal, a correct signal, what you call signal efficiency versus 0% background. So there will be some, with all the hype about machine learning, it will have its own, what we call the ROC integral, and means little bit of background will be there, and little bit of background signal you will also lose, so you'll lose some signal. So that is basically this, that how many red you are getting in your side, how many blue you are losing from your side. Okay, so so the way it works, that you have your input feature variable, or feature, this xi, those are the vectors. So that like if you are doing, let's say, Higgs to gamma gamma signal versus there are some uncorrelated two photon events coming from your various standard model background. Or like if you're doing Hebbian, you want to determine, so you have a dimension, lots of dimension, and that dimension you want to distinguish from other possible cases where you have a kaon and pion randomly picked up, right? So let's say dimension d0 going to k pi. So your final variable may be the invariant mass of the dimension or invariant mass of the two photon, where you will see a peak at 125 GeV. But then you use machine learning method to control as much as possible the standard model background, where you look at the other variable that will be affecting. So these xi's are those input variable that you will be using for the machine learning. And this is the case of binary classification, just signal versus background. And the H here, we use this P, we call it a sigmoid function, which is 1 by 1 plus e to the power minus h. And I mean, it's not the only choice, but it's quite popular choice that we use, especially in a neural network type of classification. Okay. So let me see. So yeah. So in the case of regression, you have the so-called square error function, which was like a chi-square, right? It was like y minus h x whole square. In case of classification, it is this so-called binary cross entropy loss function, okay? And which is given by this term over here, that yi ln pi, and yeah. So and I here obviously summing over all the data points that you use in the training phase. So yeah, so now you want to put all this term like a pi term, and pi is already given by the, let's say if you use a sigmoid function, right? So that given by 1 plus whatever we gave here. I'm sorry. pi 1 by 1 plus to the power that thing, and that you put it, and once you do the log of that, and you get this term, this 1 by that becomes to the power minus 1, and then that makes it plus, and this is what you get. Basically, when you say you are doing a neural network, you have several input variable, and you are training a neural network at the your computer. What it is doing, it's essentially optimizing this function that you see here. That goes, I mean, somehow we don't bother to think that what is actually going on. We take it as a black box. So the term you see here is what is being optimized on. So at the end of the day, you get a once you get a stable set of weight file, that this W's that you get is what is your last stage, and then you say, okay, training is done. I want to establish if training is good or bad. I mean, not overtraining. So then you apply those weight, but you do not touch the weight file anymore, and you use it to the independent data set called the testing set, and you should see the similar output. And how this optimization is done, how this W, the best possible values of the W weight file are calculated. We use the method called gradient descent method, which is again, don't get too much of worry about like what it means. It's just like you start with some point. You have to start from some point, and then your idea, what you want to target, what you want to find out, that with respect to the weight file, it should be optimized. So therefore, you want to find out this gradient with respect to that weight parameter W. Obviously, W is not just a single parameter. A single it is all those depending on how many input parameter and what kind of method you are using, you may have so many W's. So you go to the step, and at that step you find out what is the error function, and then are you going in the right track or not. So there is a feed forward system, like you go step by step. If you see that you are in the right track, then you continue. If you find that your error function is going in the wrong direction, you have to turn back and sort of try again. Okay, so in this process, you start from W, you go to W prime. So W prime is given by this W minus that the derivative with respect to W, and eta is called the learning rate. Okay, and so again, in your if you are using TMVA, if you are using any kind of sort of ready-made function, ready-made package to do this machine learning method, you will see at the list, you should see that what are the default value of the learning rate, what is the number of cycle, that is number of epoch, so these are the things that tells you how far you want to get in your optimization scheme. So eta is the learning rate, and it tells you that how big the gradient step you should take. Obviously, if you make it too small, your computing time will be enormous. So the thing is, you'll be hearing that these days when you are doing deep neural network, sort of the really the most complex form of neural network method, most of the thing is done in the so-called GPU-based computing, not the CPU-based computing. So this graphical user interface, I think, graphical processing unit. So this is much more advanced, and more, particularly for this deep neural network method, it is being very much useful. So in that case, you can, if you are using such a hi-fi computing thing, you can have a smaller learning rate. but then do we need such small learning rate or not? So this is something you have to make a pragmatic choice. And yeah, so this gradient descent method is what we use, and you want to get to the so-called global minima. And you can see that at each step, like if you see the bottom right plot or this top right plot, you see that you started from here, and then you want to get to this global minima, right? And so yeah, I mean, there are certain method, this momentum, these are all advanced method, I mean, more improved method. Okay, so basically, if you go to the likelihood, which is given by this your so-called what is that called, binary cross entropy, the loss function, cross entropy loss function, binary because you have only two class. So it is given by this, and then you want to find out again what we are trying to understand, that while you are using neural network to classify two classes of event, that what is the underlying optimization going on, and that this is what those things, that how do you get the loss function, how do you minimize the loss function with respect to each of the weight parameter. Okay, all right. So yeah, this is the way in the top left. You see that how you start from a point, and then you take this change the that what we said in here. You start from the weight parameter from somewhere, and then you go to the next step, and then see that what is the value, how is the your function is looking like, is it in the your right track or not, and then here you see that you are taking long step, but as you approach to the minima, global minima, you see that it becomes you have to take shorter step. I mean, because you are very close to that, so you cannot take any long step. If you take long step, you are basically the other side of the minima. So in order to reach that, in order to get that convergence, so you start with the first long step, and which is also clearly visible from this plot, right? You start from here, and here your global minima is here. So here you take long steps, but as you approach the thing, you cannot take long steps. So it takes longer time to reach there, but you have to go in a shorter step. Okay, so yeah, and I think so once you get that your decision boundary, once you get into your so-called your training phase is over, and you want to now sort of be happy, and you want to now see that whether you have done a good job or not. Now you want to go to the testing. Before you apply to the data, you want to go to the testing phase. In the testing phase, you basically look at so-called the ROC curve, where you want to look at the signal efficiency versus background efficiency. Okay, I think this is where I would stop because I'm close to 5. And Siddharth, I guess I have no time for discussion point, or I'm over time.
So maybe we can take up the discussions tomorrow, sir. Is it okay?
Yeah, sure. That is fine.
Because I
That is
see
fine.
we are right in time, and I also see Professor Deshpande already joined.
Right. So fine. So tomorrow we will.
It's okay. If it is continuation, you can use it. I can listen, no problem.
Yeah. So just I will not speak anymore. I just want to see if the student have anything they would like to sort of quick clarification. Otherwise, we'll discuss it tomorrow. So yeah. So I want to stop at this stage. So, and I would like to hear from the student.
Hello, sir.
Yeah.
Sir, I have a question regarding the regression method.
You are Hirok? Is that Hirok?
Yes, yes, sir. Yes, sir.
Yes, yes. Tell me, Hirok.
Yes, and my question is that can we estimate the error of sensitivity prediction using the machine learning earlier so that we can minimize the error that we are trying to calculate as we are using the supervised technique, and when you I am using a particular system, mainly you are saying that when we are going to the more complex system, there is a variance error from the variance term.
Right.
So,
There is,
my question is that can we minimize the error earlier?
Let's go to that term and then we can. Yeah. So this particular slide, right?
No, maybe, sir, it is in 46, maybe slide number 46. Yes, yes, this slide, sir.
Yeah. Right. So tell me what was, sorry, I forget. Huh.
Actually, sir, we get two error from the bias term and the variance term.
Correct.
Sir, I am just asking that we are using that supervised learning so that we have the data that are known to us actually. So if we using, actually we are using machine learning to predict something actually.
Correct.
So my question is that can we predict the error so that we can minimize the error from the variance term or the bias term?
So see, it is an interplay, right? It is an interplay between the two.
Sir, yes, sir. Yes.
It is not that you want to see, as you see from this, it cannot be like one-sided story. Like you cannot only sort of say I want to have minimum bias, right? Or you want minimum variance. So you want to get to the where both of them are sort of acceptable minimum, let's call it that way, right? And at that stage, you find out what is your uncertainty, like whatever your error is, right? I think I'm not just getting that your point is you want to fix one and then you want to minimize, or I mean, here, can you again just say
Yes, sir.
that
My question is that can we set the data point we needed so that we can minimize the error terms actually?
Yeah. So okay. So your point is I know my data point, and with given this data point, I want to get the best possible thing. But the important thing is, as you saw here, as you saw here. Okay. Let's look at this. What you are seeing on the right hand side. Your data points are all well known to you, and that you have, and you say, well, I know and I understand my data point very well, and I will go for the best possible fitting, or I mean, which is actually overfitting. I mean, you and so now what happens? You have in that data point, right? But are you able to see? We physicists, important thing is reproducibility and repeatability, right? Now, whatever you did, let's say whatever collider you take, you take the data. I mean, so sometimes you'll have more data. Sometimes, or someone else will look at it. Now, are you, whatever you have got, is it able to, are you able to reproduce it? But you see that if you have something like this, which is not an average, the middle one is more like an averaging and getting the sort of really picking up the trend of your data. On the right hand side, what you see, you are really doing this tiny adjustment, getting the best possible fitting, which is overfitting. Now you are prone, if you take the right model, you get anywhere else and you are screwed. Are you getting what I'm up to?
Yes, sir, I got this point.
Yeah, so you should not worry too much. No, I must really minimize the bias to the minimum. Then you get into the trouble of the variance. It's essentially like you are too sensitive for any tiny thing away from your data, you are gone. You are gone. But if you get in the average distribution, which is in the middle, then your fit is reasonably robust. Your weight parameter will be able to reproduce if you get into different data set, higher, larger data size. That's all okay.
Okay, thank you, sir.
Yeah, so already I'm 5 minutes past. So if anyone else have question, I would rather take it up in the next lecture. Before starting the formal part, 10 minutes we'll have discussion. Like I would like to ask all of you. So please ponder about the thing that we have discussed today. Some of the mathematical term may sound little difficult, but try to capture the conceptual part. Don't worry too much of the mathematics. And as I said, the whole idea is to tell you that what is the underlying mechanism, underlying method that is running behind the scene in the machine learning thing. Okay, so thanks very much, and I'm sorry for overrunning by 5 minutes. Sorry.
No problem. Thanks a lot, Professor Mohanty. And now we come to